Okay, let's start. So, so one thing I wanted to do was as a finite state machine last time around with for at the microcode, I did not have the FSM. So I want to just go over that how it kind of works out to again give you a sense of what's happening. So this is an example of a traffic light controller, which is a left turn signal. So the basic idea is, again, an original example where there is a north-south, east-west, there's a sensor on the east-west. Whenever there's a car on the east-west, we want to let it go. But now what we also have is a left turn sensor, and the idea is that the left turn sensor indicates that along the east-west route, there is a car which wants to make a left turn to north-south, then we are going to give it a dedicated left turn signal. So now we have 9 lines. I have 3 for north-south straight, 3 for east-west straight, and then I have additional 3 red, red, yellow, green for the left turn. Okay, so essentially what we want to do is, normally the north-south is green. If something comes to make a left turn sensor indicates that, then we are going to make a left, we are going to turn the left turn, dedicated left turn to be green. If on the other hand, east-west sensor indicates that there is a car which wishes to go straight has come, then we are going to turn the east-west light green, and otherwise we come back to north-south. So let's see how this particular microcode plays out. So what we have out here is total of 9 outputs because I have 9 lights, and those outputs are structured as first 3 bits indicate red, green, red, green, red, yellow, green for the north-south. The next 3 bits indicate for left turn, and the final 3 indicates for east-west. Now, what we see out here is microcode where the first column gives you the memory address. The next one is a label we have given to that address, just so that it's kind of something understandable. And then what we are doing is, let's follow through this code. So when the program starts, it will go to the very first location, address 000. We are calling it to be the state NS1. So let's try to see what state machine this corresponds to. So what we have is a state called NS1. And then what we see out here is the instruction is branch if left turn. So if the left turn sensor is indicating is 1, so then we are going to go to the target, which is has the address 0101, and it has a name LT1. So you will see LT1 is out here, and it has a address of 0101. So what's happening now is, in terms of our state machine, we go to LT1. And we are doing so if left turn sensor is true. Okay, so the LT is the signal which is coming from the left turn sensor. Okay, if the left turn sensor is not true, if the left turn sensor is 0, where would I go? So again, recall microprogram counter. If the branch condition is false, what happens to the program counter? Anyone? +1, exactly. We move to the next one. So in this case, the next one is NS2. So what it means is that the other condition, that is not LT, I'm going to move to the +1, which is NS2. So I'm moving to NS2. The other thing you would notice is in NS1, the north-south green is on. For left and east-west, the red is on. So I'm going to write it as it was green, red, red. In LT1, which is out here, it is, LT1 is out here. It's yellow, red, red. So you see it's 010, 001, 001. So it is yellow, red, red. So before turning the left turn green, we are going to make it a yellow on the north-south direction. So that's what's happening out here. You would see that how the micro instruction, which is the data part of the ROM, consists of the branch instruction, which is 001. That's the first 3 bits. So you see the first 3 bits are the branch instruction, BLT. Then the next 4 bits are 0101. They correspond to the target, LT1. And then the final 9 bits correspond to whatever my output control was.
What do you mean by target?
Destination of the branch, the address where you want to go to. So BLT says if left turn is true, go to the destination address, and the destination address is the branch target. Okay, if you recall, our micro instruction looked like this. It has the opcode, target, and outputs. Okay, so going back out here, so I can not LT I go to NS2, and for LT I go to LT1. Now in NS2 we are saying BNEW, which is branch if not east-west. So it's saying if the east-west sensor is 0, then go back to NS1. The target here is NS1. So it's basically saying from NS2 we are saying if not east-west, go back to NS1. If on the other hand east-west is true, then again the logic, same logic applies. We'll move, so the condition is false, so we are going to move to the next instruction.
Does that mean north south 2 is always like green red red because nothing changes?
NS2 is also green red red, and NS1 is also green red red.
So is it green red red because like when you plus 1 to the adder, like when you add plus 1 it just maintains?
No, it's basically in that state in NS2, if you see, the output bits are again green red red. This is something you get to decide. So we are making sure that NS1 is green red red by setting the bits here correctly, which basically are the final 9 bits of my micro instruction. And likewise, I'm doing the same thing for NS2 also. And basically what's happening is, if you see out here, if neither one of the 2 sensors are on, then I'm basically going to be flipping back and forth between these 2 states. Okay, in NS1 I check for the LT sensor. In the NS2 I'm checking the east-west sensor. And just a second. And the reason we are doing it is because I don't have any instruction which can check for both sensors simultaneously. I can check one sensor at a time. So I check the left turn sensor. If it is false, then I go to NS2. I check for the east-west sensor. If it is false, I go back to NS1. But throughout that thing, I'm keeping the north-south light to be green and the east-west and left-turn lights to be red. Okay, go ahead.
So is it kind of like in the old state tables we would have like your inputs and then your outputs, but for this one you have your state and you have your target, but then you have your state lights, which are from the original state, not the target state, right?
It's from the current state, right? So as long as I'm in NS1, think of it like essentially it's like a more kind of behavior that these 9 bits are telling me that when I am in state NS1, what are the output bits? Okay. Later on, as we had discussed towards the end of last lecture, we can play these games where instead of outputting all the 9 lights, I could have registers corresponding to them and then update only one of those lights at a time. But in this example, I have all the 9 pins going to the 9 lights, much like we were doing, much like you're doing in your design homework as well as in the problem set. Okay? And the reason we have these 2 states is because I'm unable to check for both the sensors simultaneously with a single instruction. Okay, so I first check for one type of sensor, LT sensor, then I check for the east-west sensor, and I keep doing it repeatedly. And throughout, I maintain the lights to be green in north-south direction, red in the other 2 directions. Okay, so on NS2, if on the other hand east-west was true, which means BNEW will fail its condition, then we move to the next instruction, which is EW1. So what this says is, if in terms of our diagram, that if east-west is true, then I move to an instruction state called EW1. And in EW1, you would see that the lights are yellow, red, red. So here we are yellow, red, red. And which is fine because again we detected that there's a car on east-west side and therefore we want to turn the lights that way. Okay, going back out here, let's stick with east-west 1. East-west 1, the branch instruction says no op. So what happens in a no op? What would be the next state? When a branch instruction says no op, what is the meaning in terms of our program counter? Just go to the next instruction, unconditionally so. So next instruction in this case is going to be at 0011, which is east-west 2. So east-west 1, I always move to east-west 2. Okay. And in east-west 2, you see the output is red, red, green. So now I have turned the east-west light to be green. So what I have out here is red, red, green. So east-west 1, we turn the light yellow in the north-south direction. East-west 2, north-south is now red, but east-west has become green. Now going back out here, east-west 2 also says branch if east-west. And you see the target out here is east-west 2 only. So it's saying that if the condition is true, that is if east-west sensor is high, then jump back to east-west 2, which is itself. So it's kind of a self loop. It's saying stay there as long as east-west is high. So this is what it is doing. As long as east-west is high, it is going to stay put in the same state, east-west 2. That's what is happening. Branch if east-west, back to EW2. So it's kind of like in a programming language, you say some label colon go to the same label, so you're not spinning it. Okay, but if on the other hand east-west is false, then we'll move to the next instruction, which is east-west 3. So going back out here, I have a state called east-west 3. And I'm going to that state if east-west sensor is false. So not east-west. And looking back out here, east-west 3, the output is red, red, yellow. So now what has happened is the east-west sensor says there are no more cars. So we are coming out of that one. We are turning the light yellow in east-west direction, and then we will go back to north-south green. And east-west 3 says branch to NS1. Now branch to NS1 is an unconditional branch, right? It basically says just always jump to the target address, which in this case is NS1. So basically in our state machine terms, what it is saying is from this guy, go back out here unconditionally. Okay, so all the time, just one. All the time we're going back here. So intuitively, again, kind of what's happening is I first check the left turn sensor. If it was false, then I check for the east-west sensor. If it was true, then I turn the light yellow in the north-south direction. Then I move to the next state, turn the light green in the east-west direction and red in the north-south direction. And I wait there until the east-west sensor indicates a false value. I come out of it, I turn east-west light to be yellow, and then just for one clock cycle, and then I go back to this little north-south direction where I'm going to spin there again. And similar behavior happens for LT. So let's look at LT1. In LT1, we have a no-op, and the output is yellow, red, red. So that's what we have. But if I look at LT1, its instruction says no-op. So no-op basically means just move on unconditionally to the next state, next address. Next address is the subsequent one, which is LT2. So I have LT2. And LT2 says, so firstly in LT2 you would see that the output says 001, 100, 001, which means it's red, green, red. which makes sense. I have turned the light for left turn green now. Moreover, LT2 says branch if LT is true to LT2. So it's a self loop. It's saying as long as LT is true, as long as the LT sensor says hi, keep going back to the state itself. So it basically means that I have a self loop out here, which is taken whenever LT is high. So I'm going to wait there until until there are no more cars on the left turn. Once LT is false, it will go, microprogram counter will be incremented, and I will reach the state LT3. So let's draw it out here. So I have a state called LT3. In LT3, the light status are red, yellow, red. So I'm now turning the left turn light to be yellow because I'm getting out of it. So it's red, yellow, red. And then you see the instruction here says branch NS1. Unconditionally go back to NS1. So what we have out here is I just unconditionally go back out there. So from the microcode, you can draw this kind of a state machine. And what you see out here is that we had to do the, like if I were normally drawing the state machine, I would have probably have had a single state called NS, and then I would have many branches going out of it. But since my microcode did not allow me to check for both LT and east-west together, so I had to split that state into two states. One state in which I check for left turn sensor, and another state in which I check for the east-west sensor, and I kind of keep going back and forth between the two. Okay, so firstly, you had a.
I was just trying to like thinking of the other state diagrams you showed where like from one stage you can go to multiple other stages, like instead of just two.
Right.
Can you do that with?
Not with the instruction set we had thus far in this particular one, right? So the only branch instructions we had out here are those which can let you either go to an address under some condition or go to the next address, right? So we can only do two-way branches. Then, if you recall, last time I'd also discussed that by some additional logic, we can have, like, the example I had was four-way. Those are relatively rare. But point is that unlike when I'm drawing a state machine just arbitrarily, where I can have any number of outgoing edges as I want, here I'm limited by what instructions I have. Okay. Now, if you are using a processor which is given to you, then you have to abide by whatever you have. If, on the other hand, you're designing your own logic entirely, then you can define your instructions. So, like if you decide that, I need a five outgoing edges, then I can define a five-way branch. Now, the problem that you face with microcode is that I can only specify a single branch target. I cannot specify 5 different arbitrary branch targets. So then we start playing games. We basically say, okay, I have a 3-way branch. I'm going to give the address for the first branch. And the other 2 branches, their addresses would be offset from from the first one by some fixed amount. So we can say the branch to let's say I'm checking a value of a sensor X, and I say if X is 1, go to a target address. If X is 2, go to the target address plus 10. And if 10 is just fixed into my design. And if X is 3, go to target address plus 20. Okay, so I could define instructions like these. But they are more constraining than if I were to design an arbitrary state machine where I could jump from any state to any state and have any number of outgoing edges. You cannot do that in microcode. You are limited by kind of the style of this microcode. Okay, so there was a hand there also. Yeah.
Oh yeah. So, what is it for the one with the microcode?
Mm-hmm.
It's basically just like the like which address has which memory is like really important, right? Because then it shows like whether or not if they're like linked together, then you just like go down. But in like the other like the original way that we did it, like it's just like you follow exactly where the target goes, right?
By original, you mean?
Like the one where.
Oh, the one where I did not have the branch instruction.
Yeah, no
Right.
branch instruction.
Yeah. So where I did not have the branch instruction, then for every state, I basically explicitly specified what the next state was. Right. So there I was literally like, I think this is what you are referring to, and let's just go back to it. Yeah, like this one. Here, the thing is, there is no notion of a branch instruction. There was no microprogram counter, right? So here, basically, at every state, I was also describing what the next state is. The penalty I'm paying for this is that my inputs, the sensors, are also part of my address now, right? So it was to optimize this away, which is why we kind of created this whole program counter business, where the inputs now only affect the branching logic. They are not part of the address directly. So I saved on the number of addresses I need in the memory, but then I have these limitations now that I can only specify, like in a two-way branch, I can only specify one target address. So let's go back to an example that we had out here. See out here how for each state, I have actually multiple entries in the memory, one corresponding to each of the two values of the sensor. So my state was 0, 0, but in the memory, I needed two entries, one where the input was 0 and the other where the input was 1. Right? So I actually have number of states multiplied by 2 to the power number of inputs. Right? Whereas with the whole branching approach, with the kind of thing, I basically need as many entries as the number of states.
Does that mean that, like, could you just have, like instead of having only one bit for car east-west, could you have 2 bits for car east-west?
Yeah, let's say I were to do this example with car east-west and the left turn sensor. Okay, in that case, for each state, I would have 2 bits of state here, and then 2 bits of input, which means 4 combinations. So actually, for each state, I would need 4 entries in that memory table. Okay, whereas with the whole branching stuff, I don't need to have that. So that's why, if you recall, I had this diagram which basically said, where is it? See here, the number of memory words is 2 to the power s plus I. So for each state, I also need to take into account every possible combination of the input. Whereas with the branching logic approach, the memory number of words in the memory is 2 to the power s. Because the inputs only affect the branching logic. My microprogram count, but I have this ability to now increment the microprogram counter by default or load a new value into it, which is coming from the target.
Are you basically saying that, like, for this way, you're like first figuring out where your target is, and then that's all you send to your DQ, and that's what goes into the memory. While in the previous version, you're taking both your DQ and you're taking both your input and your current state, and you're adding together and sending it through memory.
In the first one, I'm taking my current state and all my inputs, forming a vector out of it, using that as an address into the memory. Okay? And so for each state, I have now multiple entries, one entry per possible combination of input. Okay? In this approach, I have a single entry for a state in the memory, but now using the inputs, I can say what should my next address be. Okay? So I'm saving on the number of address bits that I need for the memory, because the inputs are only the state is being used to control which address in the memory I look at, but then I need all this branching logic to say how the next state should be based upon the inputs.
So it does the calculation at the beginning in a sense, right? That's what the microcoding does?
Well, both are microcode. Okay, it's just different ways of doing microcoding. The purpose is that here I'm saving the number of words in the memory. Okay, and then this branch logic needs to be carefully designed because it supports those branching instructions. So this latter approach is more like the way you write programs now, because in programs you have access to go to an address, go to some particular label. All programming languages provide it, Java, C, and all. It's just that it's frowned upon. Like normally when they teach you programming, they say you should use while loop, for loop, stuff like that, and don't use gotos or dumps because that leads to spaghetti code. You're not just jumping all over. But deep down at the microcode level, that's all you have. You have these branching instructions. Most of the time, you will have a two-way branch. Jump to a target or move to the next one. That's all you would have. And if you're lucky that you're designing your own, then maybe you have a four-way branch or a multi-way branch, but that's kind of rare unless you're designing your own.
So if you were to get like a four-way branch, would you basically increase your multiplexers by one more?
No, you could do that way, but the problem with that is where will you get the target at? Because I don't want to increase the size of my instruction, so I still want only one target address. Okay, so this is what sort of something I had described last time, but let's just go over it quickly. This is what we do. We put this little logic in front of it. Okay, and what it does is it takes my branch target and it modifies it as a function of the input. So for example, it can say if input is 0, add 0 to the branch target. If input is 1, add 10 to the branch target. If input is 2, add 20 to the branch target. You could define something so that from a single target, you can generate multiple targets. But you are constrained. I mean, whatever this logic says is all you can do out here. So this was an example I had which said branch by looking at in0 or in1, there are two inputs, and it says microprogram counter. The new microprogram counter is microprogram counter plus branch target plus 4 times the value of the 2-bit input. So it's basically saying if depending upon in1, in0, you are either going to jump to microprogram counter plus whatever the branch target said, or branch target plus 4 times 1 or 4 times 2 or 4 times 3. Okay. Very commonly found in the processors. You are constrained. I mean, now what's happening is when you are jumping to, you're jumping to one of 4 places. So let's say in this example, branch target was, hypothetically, let's say branch target was 10. And let's say, and we are looking at this. So what this means is that the microprogram counter would be, possible values of microprogram counter are going to be microprogram counter plus 10, plus 20, plus 30, or plus 40. These are the 4 addresses you are jumping to. Okay, because actually I'm sorry. Yeah, that's correct. So branch target I set to be 10. So the new value is microprogram counter plus 10 or plus 20 or plus 30 or plus 40. No, actually I'm wrong. Sorry. Let's take it back. If branch target is 10, so it becomes microprogram counter plus 10 or plus 14 or plus 18 or plus 22. I'm sorry. So it would be. So what's happening is I'm only able to jump to some specific addresses now, not arbitrary. Whereas in the first type of microcode, without the branch instruction, I could specify anything arbitrary, but then I needed more words in the memory. So that's really the trade-off that's happening.
So the difference between this multi-way branch and the previous one-way branch?
Two-way branch.
What?
Well, it's either jump to a target or move to the next one. Right?
Yes. The difference is that in the previous one, if we want to go to 2 branch targets, then we should create intermediate state, and then from that state we go to the other.
For me to jump to 2 arbitrary places, I needed 2 steps, two stages for it. That's what was happening in this NS1, NS2, right? That I was checking left turn sensor, and for that I wanted to go to LT1, and I was checking the east-west sensor, and I wanted to go to east-west one. So I had to take my state, which is conceptually a single state where I want the light to be green, red, red. I have to make it into 2 instructions.
This version is
I don't know whether it's improved or not, depending upon the example. One may be better, the other may be better. I mean, it's always a trade-off between the program size versus. I mean, they're just different ways of doing it. And again, a lot of times you don't have control over it. You are given. I mean, the rest of the stuff has already been designed for you. Micro instruction format is fixed. All you are doing is writing a program. On the other hand, in early stages, when you are designing the chip or the system, then you are designing the micro instruction also, in which case you can have more flexibility. Any other questions on this one?
So for the with the branch targets, like I'm talking about the most complex way, like it's we have 2 to the s plus I,
Mm-hmm.
and then that's because multiple inputs go to the same state, then we have the memory is increased.
Well, it's not that multiple inputs came to the same state. The thing is, if you are in a state,
We have multiple.
you are observing multiple inputs. And if I have 5 inputs, then I have 2 to the power 5 possibilities out of that state. Right? In the worst case, for each unique combination of input, I may be taking a different edge. Right? So if I'm in a given state and I have 5 input, 5 bits of input, then I can have as many as 32 edges out of that place.
So for the memory with the branch logic, the size of memory is the same as the number of states, right?
Size of memory is the same as number of states. That is correct. The only thing is that I may have to split states, so I may have some more states now, right? Because as we saw that this NS state, NS being green state, I actually had to make 2 states out of it. So I may need a few more states, but overall I'm much ahead. Okay, so this style of kind of creating sequential systems, as you can see, software people like it a lot because it becomes kind of like writing a program. So it's more limiting, but arguably it turns out to be easier. And more importantly, what happened was, if you recall, one of the very first slides I had shown was this gentleman, Morris Wilks. So very first computers were actually microcoded computers. That's when kind of the notion of microcode had come. In fact, that's why the name microcode, microprogram. So what happens is that really what we are doing is we are essentially creating very specialized computers out here. And so indeed, so we started out where ROM was playing the role of just a combinational logic. Then we kind of added these complexities like branch logic and then branch and load, where we were loading stuff into output registers, which I covered last time. And then a regular computer is just the next step. It's a full instruction set. As in, like, again, in some future course, you'll see that computers are nothing but they specify what they call as instruction set architecture, which is nothing but they give you the coding like my instructions are 32-bit. Some bits will be the code, opcode, operation code. Some bits will tell what action is being taken. Or they will tell where to jump, things like that. So that's how a computer's architecture or microarchitecture, as they call, kind of look like. So you would see things like, if you look at a description of a processor, you would see things like there might be instructions called like an add instruction. An add instruction may say, somewhere in the computer are a bunch of registers where you store variables. They typically are labeled as R0, R1, R2, so on and so forth. And then there might be an instruction which says, I can add 2 registers and deposit their result in a 3rd register. So most computers will provide some instruction where a few bits will tell what operation is being done, let's say add. Some bits will tell what is the first operand, which register is the first operand. Some more bits will tell what is the second operand, and then some bits will tell you what is the ID of the output. So typically what happens is in a computer, you are going to have what are called as register banks. Register bank is nothing but a little memory, okay? Except that's a writable memory. So in this case, let's say I have a register bank with 4 registers, 0, 1, 2, 3. Each one of them is, let's say, a 32-bit number. And then I may define an instruction where first 2 bits may tell what operation it is, let's say. So first 2 bits can tell, or let's say first 3 bits. So let's say 0, 0, 0 may indicates it's an add. Next 2 bits may tell what is the first operation. So I need 2 bits for it because I have 4 registers. So it tells me op1. Next 2 bits may tell me op2. So, and then the final bit may tell me the result. Which register is the result? So what's saying is, this is saying add, let's say. It's a made up example. So 0, 0, 0 stands for add. So this is saying add register number 0 to register number 1 and store the result back in register number 0. So it is basically doing register 0 gets the value register 0 plus register 1. If I wanted to add, let's say, register 1 and register 2 and store it in register 3, then my instruction would look like 0, 0, 0. Register 1 is 1, register 2 is 2, register 3 is 3, and this is doing R3 gets the value R1 plus R2. Then these first 3 bits, my computer may also provide for, let's say, subtraction. So maybe 0, 0, 1 may be subtraction. And I may have multiplication and division and stuff like that, other operations. Then in the same instruction, so remember my instruction set now is 3 plus 6, it is 9 bits, kind of an odd number, but let's say it is that. Then maybe I can have a branch instruction. So maybe let's say 111 may stand for branch, and then the remaining 6 bits may tell me the address, the target to which I am branching to. So when you look at a computer, you would see that they will define these sets of instructions. They will have a very particular coding. The data sheets will describe that. There will be arithmetic operations. There will be operations to jump to different places, and a bunch of other things. Operations to support subroutines. There are always some special registers in the computer, for example, doing I/O and all. So all of that tends to be provided in a typical computer. There will also be instructions like load and store. What they do is they take the data from your registers and put them into the main memory of the computer, the big DRAM, or vice versa. Take something from the DRAM and move it into one of the registers. Why do you think we don't do arithmetic directly on contents of the memory? So like I showed how I can do addition on 2 registers and put the output into another register. Why not take contents from the main memory or DRAM, add them up, put it back in the main memory? Speed. They're too far away. For a modern high-speed computer, it takes milliseconds to get to the DRAM, where it takes nanoseconds to get to a register. Okay, so huge difference. In between, there is also something called cache memory, which is a faster memory, faster, smaller memory, to which it takes, again, maybe, let's say, hundreds of nanoseconds kind of thing. So there are, the bigger the memory, the slower it is going to be, and the farther away it is going to reside. So what you see typically is that modern computers, they provide operations on the registers. They'll have tons of registers. In this example, I had 4 registers, but usually they'll have 32 or 64 registers, and then they do operations in that. Go ahead.
The register you're talking about on the CPU, right?
On the CPU, inside the CPU, yeah.
Is that like
So it's in your data path. Yeah. Any other questions? This example, load R2 gets the value M, R1, R0. What this is saying is, take the content of R1, take the content of R0, add them up, use that as an address to your DRAM. M stands for the memory, the main memory. So main memory is again like a gigantic table, and what we are doing is we are adding R1 and R0. We are using that as an address to the main memory, going out to the main memory, getting the data, and putting it into register R2. The store does the reverse. It takes the content of R2 and puts it into a particular location in the main memory. It's kind of like all of you have calculators. In your calculator, usually you have a button called store and recall. Sometimes it has multiple memories in it. So you can store intermediate results. So that's the kind of thing that's happening. Your working value, which is on the display, you can store it into a memory location, and later on you can recall it. So calculators are nothing but very simple CPUs. In fact, they are CPUs. They just are low-end computers. And in calculators, obviously, you see your add operations and these kind of operations also being there. So that's basically what's happening. And when you press those buttons, they basically result in some instruction being executed on the CPU of the calculator. What an instruction does, whether it branches or does an addition or stores into the memory, that's called opcode. So here I have an example where maybe 000 stands for branch, 001 stands for load the register from memory, 010 is addition, 011 is, okay, I don't know what LDR is, I forget. Add, load, store, stuff like that. What typically when you, again, as I said, when you buy a CPU, it comes with a fixed instruction. But when you are designing your own chip, then you can define the instruction. And then you are designing a processor whose instructions are customized to your application. And there are tools which help you do that. So for example, maybe let's say my application uses a lot of, I don't know, some complex operation. Maybe it needs to take sine and cos of angles a lot of time. So maybe I can define a processor that sine and cosine are instructions. Normally they are not, because they are rarely used. You can fake sine and cosine by doing addition, multiplication, subtraction, and all. But maybe for particular application, maybe I'm doing a computer for, I don't know, missile or target tracking or something where a lot of trigonometry needs to be done, then maybe I'll create a special instruction for these operations. So in some cases, instructions get defined by you. More common nowadays is to buy a processor which comes with a fixed instruction set, and then you write software for it. So deep down, software, hardware, that boundary is actually an artificial one, as you can see. If you are doing hardware with this microcode way, it's really as if you're designing your own processor and you're writing software for it. Whereas if you are writing software, when we say you're a software engineer, you're writing software for a hardware that someone else designed for you. That's really kind of only different. Otherwise, it's the same thing that's happening.
So are you saying that, like, the person that defines these, like, codes, right? Is that a software thing or is that a hardware piece?
It's what are called as computer architects. Okay, so they are. You will find them in the computing part of EE departments and in the hardware part of CS departments. Okay. Depends on the university. I mean, this is where the two fields meet. Okay? And again, like you cannot escape this in a CS department.
So you're saying like these branch instructions, right? Is it like in order to make the address memory thing, is it like you load software onto the hardware in order to create these instructions?
There are two ways of doing it. So this microprogram memory, microcode memory, may be a writable memory. So when you write your program, you burn it into it. Okay. So nowadays, typically, it could be flash memory. But the advantage is I power it off, the program is still there. Okay. On the other hand, if it is a RAM, then every time you power off, replace battery, you have to rewrite it. Okay. So that's the second approach. The third approach, which is when the chip is being designed, you burn it into the silicon. But that is less common nowadays because then you are foregoing the possibility of changing the microcode forever. Okay, but it's done. Any other questions? Yeah.
The reason I asked you the size of the memory is the number of states, and that states should also include the output. The state are the state plus the output, which is the combined.
No. The content of the memory location has the output, right? So when I'm in that state, I'm outputting some value. So if you go back to this example that we were doing, or let's take, look at out here. I mean, this is another example, but at each address, I'm storing the next state, and I'm also storing the output bits. So the memory content of the memory, which is this guy, the final 6 bits in this case are the output value.
So I'm asking, this data should be treated as a state, and the memory side should have as many data as many.
No, this data is not the state. The state is the number of distinct addresses I have. This data is, remember, this memory is implementing my combinational logic, right? Originally in my sequential thing, I said all sequential logic can be implemented as a table lookup, right? So this content is representing the combinational logic, which is corresponding to next state logic and the output logic.
Let's say we have 9 different data, then the memory size should be 9.
Thus, if I have now 9 output bits, and let's say I have 4 bits of address, then in this particular case, then you would see it will be 4 plus 9. Right? I mean, each instruction has to give me what is the output, and it will also tell me how to get to the next state.
I'm just asking the memory size.
You were not asking memory size, you were asking, is it the state? No, it's not the state.
So now I'm asking memory size.
Memory size is going to be, so number of words in the memory multiplied by number of bits at each location.
And the number of words is the number of data.
No, not just that. It also has the branch code and the branch target. Right? This one. So branch instruction plus branch target plus the output bits. All of that has to be stored at that address. Right? And originally, like the very first examples we had started out with, it was a next state. So it was, before the branch instruction, it used to be S plus O. S for the next state, O for the output. Now I have some additional bits to encode the type of branch. Okay, so one of the homeworks I'm going to be handing out, I'm going to give you a data path, and you'll have to write the microcode. So you'll get to see, it's really kind of programming at a very low level. This will happen. So you'll get some exposure to that. So the thought I just wanted to leave you with is that a processor, which many of you will encounter in follow-on courses, is nothing but a sequential system with a fixed instruction set, and then you write software for it. That's all. You're really kind of coding. When you write software, you're really designing a sequential system. And if you are an EE or a computer architect, then you may design processors where you get to design the instruction set. Okay, so microcode is basically, to summarize, microcode is a way of designing sequential systems. It's nothing but a state machine where the combinational part is now implemented using a memory, either a ROM or a RAM. We saw different ways by which you can optimize the size of this memory. Couple of insights that they make use of is, one is, most of the time we jumped to the next state, the following state, which was numerically +1. So that led to this notion of microprogram counter and a branch instruction. And the other one is, most of the time we don't change all the outputs. So therefore we put registers in the output and then selectively write to them, that we saw last time. And really you're basically just a few steps away from having a complete processor as a result. Yeah.
Does that mean that for the design project 3, you could have actually put in microcoding for
You
a
could.
machine?
Except that I had not taught you then, but you could have. Absolutely. You want to do it again? And in fact, I mean, when you buy, I would encourage all of you, like particularly those of your E's, when you buy these kind of things and all, maybe once in a while open them and see what's inside. You'll see that these digital locks have nothing but a little processor in them. That's how they are implemented. They don't do it the way we did it. It's a lot cheaper to develop software than to develop hardware. Any other question before I move on to the next topic? Okay. So, okay, so the next thing we are going to cover is time. So thus far, by and large, we have ignored the fact that these circuits are physical things. And so when they operate, they take some time. We had some early discussion about delays through combinational logic, and then we kind of talked about the clock summer period or something like that, but we really kind of didn't go much into that. So this whole discussion is going to be about that. So as you saw that we like to design systems where there are clocks and the clocks drive the flip-flops. So a natural question which comes up is how fast can the clock be? So a clock is, if you noticed in like logic sim, is essentially a signal which oscillates between 1 and 0. So you can think of a clock as a period, which means the time gap between two successive rising edges or equally well two successive falling edges. And then that's called one cycle of the clock. And some fraction of that cycle, the clock is high. Rest of the time, the clock is low. So there are basically two parameters of interest. One is the period of the clock, and the other is, you can say, the duration of time the clock is high, or the pulse width of the clock. And a question that comes up is, when you design a circuit, can I run it any clock speed? And obviously we know we cannot, because when you buy a processor, it comes with things like it's 1 gigahertz or 3 gigahertz and whatnot. And nowadays when you buy processors, for a number of years lately, we have been stuck at around 3 gigahertz or so. I mean, or even lower. I mean, even like the Intel processors in the Macs have been buying in recent years. Maybe they go to 3.2 gigahertz or something like that. Tinier processors in your smartphones, like they are around 1 gigahertz or so. The clock speed tends to be around that. So when they say clock is 1 gigahertz, this is what they're referring to. That the clock period is, or whatever frequency, which is 1 over t, is that much time. So the question of interest is, given a piece of hardware that you have designed, what clock speed can I run it on, and what dictates those clock speeds? So what the issue that happens is the following. So kind of let's go back to how the sequential circuits were operating. So all sequential circuits, if you recall, look like this. There's a combinational logic which takes as its input the input coming from the outside world, as well as the value of the current state, which is coming from the state register, the flip-flops here. And then it produces two types of outputs, the output which is headed to the external world, as well as the output which is really called the next state, which goes back to the state register. And looking at this, and furthermore, we knew that the state register, every time there's a clock edge, it reads the next state and puts them in. So how fast can a clock run? One answer to that is that next state should be ready before the clock tick comes, right? So if I'm running the clock at, let's say, 1 megahertz, then the period of the clock is 1 microsecond, which basically means that as soon as I have a clock tick, I have a new value on the current state, and then the effect of that, any change in value, and for now imagine inputs are stable, any change in value should flow through this combinational logic and become ready in time for the next clock tick. If I'm too slow, then I'll miss the next clock tick. So answer to how fast a clock should be really is about how fast my combinational logic is, and perhaps also something about my flip-flop, how fast does the flip-flop react. So we'll see how that kind of plays out. So the change in current state logic percolates through this combinational logic and then appears out here. And as we also saw early on when we talked about hazards and all, what may happen is that the output may change multiple times before settling. So if I look at a combinational logic, I change one of the inputs. What may happen is the output may change and then change again before it settles. So there might be a lot of ups and downs on the output before the output settles. So really, intuitively, the two things that we have to worry about. What is the first, after I change an input, what's the earliest the output changes, and then how long does the output take to stabilize? Okay, so taking into account all those hazards and other sort of transitions that may be happening. So what we need to make sure is that the next state becomes stable just before the next clock edge comes. Otherwise, the correctness of the whole assumption that I have is that every clock tick clocking it, I'm latching the next, I'm storing the next state will be low. So I have to make sure.
Does that mean like the limiting factor for why like you can't go higher than 3 gigahertz is because the combination logic doesn't stabilize quick enough?
Actually, it's a number of things, and actually, it is we don't talk about in this class at all. But wires have delays too, and it's actually the wires at those tiny chip sizes. It's actually the delays in the wires which are okay.
Is it possible that the next state updates right at the update?
You cannot have it. So we'll very soon see it. In fact, if they happen while the clock edge is coming, really bad things happen. Okay. Any other question? But excellent question, and actually, if you are on the circuit pathway, you'll probably study it in some more advanced courses. Okay, so let's take an example, a counter. We have seen variants of this previously. So I have the state register for the counter. Output is the same as the state, and every clock tick I add 1 to it and feed it out here, and I can optionally reset the counter. So there's a reset signal out here. So what's happening out here? If I look at this clock tick, so now we are going to consider that all these things have delays, right? I mean, this combinational logic, which is adding +1, will take some time. This multiplexer will take some time. So what will happen is this clock tick is going to result in a new value being stored into the flip-flops, whose output will appear out here after a little bit delay. Flip-flops also have delays. So when the clock tick comes, the effect of the clock tick on the clock edge on the output is not immediate. It would be a few picoseconds or so, but it would be some time. So clock edge comes, the flip-flop take the value on their input wires, store it in the flip-flop, and the output appears on the output wires. There will be some tiny delay. So that's this delay that we are seeing. This delay out here, if you see the first from the clock edge to the first dotted line, that is the delay in the D flip-flop. So after that tiny delay, count has become stable. Then the effect of this count is going to go through this adder or this incrementer and through this multiplexer, and then the next value is going to become stable after some further delay. So this second delay, which you see out here, is the delay delayed through the next state logic. So delayed through this +1 and through this multiplexer. So after every clock tick, the new value of the value at next will become stable after some time. And what we need to make sure is that this time by which it is stable is earlier than the next rising edge. If it is not, then my circuit will not function correctly. So now let's look at what happens. My states may have multiple bits. So let's say my state.
You said next has to stabilize before the.
Yeah, because remember, the flip-flop's job is that at the next clock tick, namely at this clock tick, this flip-flop will take whatever is here and latch it in. So the input better be ready by then, right? So that's what we seek to do. Okay, so now imagine my state had many bits. Let's say the state had n bits. It was an n-bit counter. Then what may happen is if I look at an adder, remember how we designed the adder where I had bit 0, the carry out of bit 0 fed into bit 1, the carry out of bit 1 fed into bit 2, and so on and so forth. As you can imagine, if I make a change in the very first bit of the input, its effect will flow through all those adders, all those full adders, and then eventually appear at the most significant bit. So as I look at the output, my LSB, least significant bit, may change very quickly. whereas most significant bit may take some time to change. So if I change the inputs to the adder and I'm observing the output, I'll see that the input bits change and stabilize before the lower bits change and stabilize before the upper bits change and stabilize. So the delay from input to output is not the same for all the bits, and moreover could be dramatically different. So like for example, let's say my full adder had a delay of 1 picosecond, let's say, and I was doing a 32-bit adder, and I changed all the input bits at some time t. Then at the very least, you can imagine that the output bit number 0 will change after 1 picosecond. But output bit number 63 may take as much as 64 picoseconds to change, right? Because the effect has to flow through all the 64 bits. So if someone is an observer looking at the output bits, it would see that the output bits, they are changing at different times. So different bits of a state vector may have different delays through the next state logic. So increment n bit number by 1. This is what's happening. So an incrementer is nothing but a bunch of half adders. So this is the situation we have. I have n bits of input and I have 1 out here. And now I'm incrementing it. Okay. So what will happen is, so the A changed, and then the output sum, S of 0 will change first, and then the effect of this change will possibly flow through this carry, and then S1 will change, and then it will flow through, and eventually at the end S of Sn minus 1 will change in the worst case. So lower bits stabilize before the higher bits do. And more generally, if I have a combinational logic which has many output bits, not all of them have the same delay from the input. Some of them will change very quickly, some of them will change later. So if I look at a 2-bit counter and I look at so what's happening out here is I have the count, which is going from 0, 1, 2, 3, because it's 2-bit, and I look at how the states would be changing. So let's say I count as 0. So 0 is going throughout here. I have 0 plus 1. So next state is going to be 0, 1. But what you would see, these are the 2 bits of next state. So one is, let's see, this is next one. And this is next 0. So what you will see is I think my diagram is a little bit messed up out here. But the main point I wanted to make out here was that the 2 bits of next are not changing at the same time. So every time I update, a clock tick comes, the count will change, and a result of that count change will flow throughout here, and then the 2 bits of next will change, but the 2 bits of next may generally speaking not change at the same time. So if someone is looking at the next, it's looking at those 2 bits, then it sees that the next is changing from 1 to 2 to 3 to 0, but in between, the 2 bits of next are going through some arbitrary values, right? So if I'm observing this state out here, at next, every time it changes, in between it goes through some unexpected values. So it may be in this example out here, it was at 1, and before it settles at 2 because it's incrementing, there will be a time in between in which it may go through some illegal values. It may go through 0 or 3 also before it settles at 2. So whenever I'm looking at a multi-bit signal, not all the bits change at the same time, and therefore there will be some time duration in which some of the bits may have changed, others have not changed yet, and therefore the overall value of that multi-bit signal may be an illegal one. And what we want to make sure, so looking at this, what you see is that every time count changes, after some time, next begins to change. That's the earliest change that is happening on next. And then after some more time, next stabilizes. So generally speaking, a signal may change very quickly and then go through some illegal values before it stabilizes at the correct value. So whenever I'm looking at more than one bit, so if I send you 32 bits, let's imagine the following. Let's say I have 32 wires running from here to you. And I put a new set of 32 values on my end of the wire right now at some time t. But now imagine these wires have different delays. So by the time the bits reach you, the bits on the faster wire will reach you first. The bits on the slower wire will reach you later. So if you're observing your end of the wire, you will not see all the bits change together. You will see some bits change earlier, some bits change later. So now every time now let's imagine I send a word at t equal to 0. Those bits arrive at you and your wires have settled, let's say after some time to that value. Then I send a new word at t equal to 1, new set of 32 bits. So if you're looking at your end, let's say the first word I send was, let's say the value 5. And let's say the next word I send is the value 7. Now what may happen is that since the delays on the different bits are different, you may see your signal not change from 5 to 7, but it may change from 5 to something else before it becomes 7. Because different bits are changing at different times. So in the example out here, next, which is a 2-bit number, is supposed to change from 1 to 2, but in the middle it may go through some undesired values out there. Yeah.
Is that caused by the adder or the multiplexer? Adder, right?
The adder would be the primary culprit out here. Yeah. But it could also happen because of the multiplexer, because maybe different bits of the multiplexer don't have exactly the same delay. Okay, so it can happen through anything, but adder clearly would be a big culprit. Okay, so so the short story out here is that when a multi-bit signal changes, then there are two things you are worrying about. So you had a valid value on it, valid current value, and it's supposed to change a valid new value. So sometime after the clock edge, the valid old value will start changing, but not all bits would have changed. So I'll go through some time in which my signal is totally jumped before all the bits have settled, and now I have a valid new value. So between valid old value and a valid new value, I may have some duration of time in which the multi-bit signal makes no sense to me. So that's what's going on out here. So what that leads to is that there are two timing parameters that are of importance to us. One is called propagation delay and the other is called contamination delay. Propagation delay says time from the last input change until the last output change. So let's imagine I have this combinational logic. I have a signal A out here and I have a signal B out here. And signal A is a multi-bit signal and signal output B is also a multi-bit signal. And let's imagine the bits on A all changed. Propagation delay says, since the last bit changed out here, to the time the last bit here stabilized, that is, whichever bit was the last one to stabilize, that delay is what we are going to call as the propagation delay. So let's imagine I was observing A and B. So A changed from some value to some new value. So this is some value A old, and this is some value A new. In between, A went through some illegal values. And because of this combinational logic, I started out with B old, and I ended with B new. And again, B also will go through some illegal values in the middle because it's this multi-bit signal. Propagation delay is the delay from the last input change, which is T3, the last time instant at which input changed, which is T3, until the last output change, which is T4. So this propagation delay is this value TDAB, delay from A to B. So that is a time gap between T3 and T4. And then we have another parameter which is of interest, which is called contamination delay. Contamination delay is the time from the first input change, so the first time A changed, which is T1, until the first output change. So the output B changed at time T2. So time gap between T1 and T2 is called T contamination between A and B. So input contaminated to output contaminated. So the first time the input changed to the first time the output changed. We call that contamination delay. And last time the input changed, when the input became stable, basically, to the last time the output changed, that is when output became stable, that we call as the propagation delay. These are just definitions.
What's the criteria to say the output is stable?
After that, until the next clock edge, it will remain stable. Right? So basically, all the effects of A changing have now taken place in output is stable. Or another way of saying is, after that time instant, if A never changed, then B will also never change. So again, thus far what we have is just definition. So this is how contamination delay, and propagation delays are defined. One is input stable to output stable, and the other is input beginning to change to output beginning to change. Okay, now in real circuits, with real silicon transistors and stuff like that, what also happens is, remember very early in the course we talked about that how logic 0 and 1 are represented using electrical signals, particularly voltages. So we often designate like a particular band of voltages is 0, another band of voltages is 1. But voltages cannot change instantaneously on a wire. Actually, why can they not? And why can I not change value immediately? Someone else? Anyone else wants to tell? No. Okay, go ahead.
Is that just because some material has some things called capacitance?
Yes. The capacitance is like a mass attached to a spring. Okay, it just makes the whole thing sluggish. So capacitance is something which you should have seen in your AP Physics B, C, or just high school physics or Physics 101 or whatever it's out there. These are essentially one of the three main types of electrical elements, which basically cause sluggishness. They are charge storage devices, and they take time to move the charges around. So they just so wires have capacitance to the ground, to the earth. When you change, wires have capacitance between wires. On a chip, wires have capacitance to the silicon. So whenever you change the voltage, what you're doing is you're charging a capacitance or discharging a capacitance, and that takes time. So it cannot happen instantaneously. So if you were to observe using an oscilloscope, which is an instrument to measure electrical quantities, you would see that the waveform at A would change a little bit like this, and the waveform at B, this is an inverter as you can see. So if I'm monitoring A and B in, then they will kind of look like this. They are not like our nice vertical edges. The edges themselves are now all smeared out in time. These delays, by the way, can be in picoseconds, or if the capacitance is very big, they can even bump into a good fraction of a nanosecond. So given that the edges are like this, it also begs the question, how do I measure delays? We define delay of clock period. Like my clock doesn't look like these sharp edges. They are these very leisurely changing edges. So how do I kind of do that? Well, it turns, the definition is electrically, delays are measured from the 50% point of the voltage swing. So if the signal is changing from, let's say, 0 volt to 1 volt, then we are going to measure the delay from 0.5 volt to 0.5 volt. That's how we define it, okay, convention, and kind of intuitively kind of makes sense. Okay, so again, that's a bit about real circuits. Going back out here, now, let's imagine I have two combinational logics which are in series with each other. So the output of one is feeding into the output of another. So I have this first combinational logic CL1, and it has input A and going output B, and then I have combination logic 2 which has input B, output C. So each one of them will have contamination delays as we defined earlier, and each one of them will have their own propagation delays. When I put them in series, contamination delay of the overall circuit is the sum of the contamination delays of the two circuits, and the propagation delay of the two circuits is the sum of the propagation delay of the two circuits. You can intuitively try to reason about it. So contamination delay is the earliest change in the input to the earliest change in the output. So let's say the earliest change in A happened at some time, then TCAB, T contamination from A to B later, B will begin to change. And then TCBC, which is contamination delay from B to C, C will begin to change. So total contamination delay would be TCAC, which is saying that if A begins to change, then as early as TCAC, C will begin to change. So the contamination delays add as you put circuits in series. Propagation delays do the same thing. Propagation delays add as I put circuits in series. So again, you can intuitively say that if the last change in A to the last change in B was TDAB, then from the last change in B to the last change in C, if it was TBDC, then naturally have to kind of add up. In the diagram you see out here, A begins to change. So A begins to change at this point, and as a result, B begins to change at this point. And so that is the contamination delay from this point to this point. And then after B begins to change, another contamination delay later, C will begin to change. So the total contamination delay is going to be from this arrow to this arrow out here. And likewise, propagation delay, when A stopped changing, last change in A to the last change in B, that is for the first stage. And from this point to this arrow is the last change in C. So this total gap is the contamination, is the propagation delay of the two put in series. So contamination delays add up, propagation delays add up. So given combinational logics with known contamination delay and known propagation delays, if I start putting them in series, you can come up with contamination delay and propagation delay of the new circuit. Now, what about circuits with parallel? So if I have two circuits in parallel, what I mean by that is, imagine I have a signal A which feeds to this circuit and also feeds to this circuit, and I'm now looking at the output, and I combine them into a single bundle of wire, and I'm looking at this. So I'm going from some signal A to some signal B out here. What would be the contamination delay? Well, if you think about it, the contamination delay, I'll have to take the minimum of the two, right? Because if A begins to change, its effect would begin to be felt at the output of the lower block. So let's call this thing the upper block and lower block. The lower block will start changing after some time, and likewise the upper block will also start changing sometime. If I'm looking at the two together, I have to take the minimum of the two. So in parallel, I have to take minimum of the contamination delays. For propagation delay, it would be the maximum, because after A stopped changing, there will be a time before which output of U will stop changing, and some other time after which output of L will stop changing. If I'm looking at the two together, I have to take the longer of the two to say output is stable. So I have to take the maximum propagation delay there. So when I'm putting combinational logics in parallel, then contamination delay of the two put together is going to be the minimum of the two, and propagation delay of the two put together will be the maximum of the two. If on the other hand I put them in series, then contamination delays add up and propagation delays add up. Question?
When they're in parallel, does that mean that they should start at the same time?
When they're in parallel, then
Should this delays start at the same time?
When they're in parallel, input A, they share the same inputs, let's say. Okay, so A changes at the same time. Okay, but the effect on the output would depend upon the individual contamination and the propagation delays. But someone who is observing the two outputs together as a single output, then for contamination delay, you have to consider which one started changing earlier, and for propagation delay, you have to consider which one stopped changing the latest. So so we have two parameters that we characterize the timing by: contamination and propagation. When you combine them in series, they add up. When you combine them in parallel, then contamination takes the minimum of the two values and propagation takes the maximum of the two values. So let's take an example. I have this little combinational circuit where I have a AND gate, I have a NOR gate here, and I have this OR gate out here. And what you are given out here is propagation delays. It has a propagation delay of 1. Let's see. Propagation delay of 1 out here for this. And so for the very basic gates like AND gate and NOR gate, the contamination delay and propagation delay tends to be the same. So you are given only a single number. It's only for more complicated things that you start seeing. So for basic gates like inverter, you'll be just given a delay, and it is both contamination delay and the propagation delay. So what we are given out here is that I have an AND gate with a delay of 1, I have a NOR gate which has a delay of 3, and I have an OR gate with a delay of 1. And if I look at the timing diagram, so like this out here, A changed, 1 time unit later D will change, and meanwhile B and C have been kept stable. So 1 time unit later B changed, and then as a result of that D changing, F will so this is what the value is. So A, let me just make sure, D goes from 1 to 0. Okay, so B is 1. Okay, so what is happening is, so B equal to 1, constant held throughout. A changed from, A was initially 1, and as a result D was initially 1. But then at this time instant, A started changing from 1 to 0. After 1 time unit, this 1 time unit is because the delay is 1 out here, D will change. D will go from 1 to 0. So D is 0 at this stage. So D becomes 0 at okay. Meanwhile, what's happening is, if you A was originally 1, and A is changing from 1 to 0. Since A was originally 1, the output of this OR gate E would have been 0, right? This NOR gate. Now, when D went down, whereas D was originally 1 and D went down to 0. So the effect of this D going to 0 will really be nothing. It will kind of remain at, let's see what is happening. I think I'm getting some values wrong. Yeah, originally F was 1. When D, in this case 0, so when D went from 1 to 0, after a delay of 1, so which is this delay 1 out here, F will go down to 0 because we'll go from OR of 1 and 0 to OR of 0 and 0. So after a delay of 1, F will change to 0. Meanwhile, what will happen out here is the effect of this change in A going from 1 to 0 will be visible at E after 3 time units, which we are seeing out here. So you'll see after a short while, E will go back to 1, and then F will go back to 1. This is actually the example of our hazard that we had long ago. That what we are seeing here is that F should have stayed from 1 and remained stable at 1, but we are seeing a little bit of a glitch in F. F went down to 0, came up to 1. Go ahead.
You have to have some sort of like initial condition, right?
Yeah, the initial condition is here, right? This guy.
So I'm just asking if you weren't given some sort of initial condition, there'd be no way of knowing.
You will always be given. You'll always be given. Okay.
So the propagation delay is so
propagation delay is so long because?
Only 8 changes. That's why the propagation delay.
Yeah, I mean, this is a contrived example out here, right? I mean, other values are set to specific things so that when A changes, what we are seeing is that output F, even though before and after value is 1, but it goes through this change, okay? So looking at this, after A changed, we see that output F began to change after time 2, and it became stable after time 4. So from the timing diagram, we see that the contamination between A and F takes 2 time units, and delay between A and F takes 4 time units. For primitive gates like AND gate and all that, the 2 delays are the same. If I were to look at this and I were to go with my approach of series and combinational kind of, so look at all the paths. Look at the path which goes from A to D to F. A to D to F, what I really have is I have this gate and this gate in series. So contamination delay is going to add up, which is 1 plus 1, 2. And propagation delay is also going to add up, which is 1 plus 1, which is 2. The other path I have to worry about is AEF. AEF contamination delay is going to be 1 plus 3. 1 for this and 3 for this. So contamination delay is 4. And propagation delay is 4 because, again, 3 plus 1 is going to be 4. So along the path ADF, I have contamination delay 2, propagation delay 2. Along the path AEF, I have contamination delay 4, propagation delay 4. I have 2 paths. The 2 paths are in parallel. So their contamination delay, I have to take the minimum one, and the propagation delay, I have to take the maximum one. And therefore, for the whole circuit, contamination delay is 2, propagation delay is 4. So the basic idea becomes, given a combinational circuit for which we have given you primitive gates, you find all paths which go from inputs to outputs. For each path, you are going to find the contamination delay and propagation delay, but that would be simple to do because if I have only primitive gates, I just add them up. And then for the overall circuit, contamination delay is going to be the shortest delay through the path, and the propagation delay is going to be the longest delay through one of the paths because those paths are all in parallel. So intuitively, what this kind of makes sense, right? Contamination delay is the earliest change, so therefore it's a fast path, and propagation delay is the latest change, and therefore it is the slowest path that we have. So in this example, for the overall circuit, I end up with contamination delay of 2, propagation delay of 4, which kind of the timing diagram also seems to indicate. Okay, so starting from primitive gates for which the 2 delays are the same, as I make bigger and bigger combinational circuits, I can keep track of contamination delay and propagation delay and keep coming up with the corresponding numbers. So let's look at this problem. So what we want to find out here is what is the contamination delay and the propagation delay through this whole circuit.
Why is contamination delay and propagation delay same for
This is a reasonable assumption to make, strictly speaking not true. But it's a very commonly used assumption to make because the difference is going to be very small. Okay, so looking at this, how many different paths we have from input to output? No, 3. Right? We have to consider, but since we are only considering from A to Q, so only 2 of those paths are relevant to us. Okay, so I have 2 paths now. One which goes like this. What is the contamination delay on this path? 25. And what's the propagation delay? Also 25. How about this path? What's the contamination delay? 65. And propagation delay is going to be the same thing, right? For the overall circuit, what's the contamination delay? Minimum of the 2, 25, and propagation is going to max out to 65. Okay, so that's kind of a simple example out here where by starting with these primitive gates, combining them, I can follow these rules to kind of get for the overall circuit the contamination and propagation delays. Okay. Full adder. You can play kind of same game out here. You can, so now generally speaking, I will have to find contamination and propagation delay between every pair of input and output. So in case of a full adder, I have A, B, and C in as the 3 inputs, and I have S and C out as the 2 outputs. So I can ask for propagation delay from A to S, contamination delay from A to S, propagation delay from carry to S, and contamination delay from carry to carry, C in to C out. And usually you are given things like 9.2 has gate delay of 80, OA121 is basically referring to this kind of a gate structure out here. Okay, this gate structure, which is an OR of an AND. Okay, so this gate structure is this guy. So what you see in this whole circuit, I am using a NAND gate, NAND 2. This is the 2-input NAND gate, and I'm using 3 copies. I'm using 2 NAND gates. I'm using Q1 and Q3, and I'm using 3 copies of this OAI21 gate. Okay, you'll find that libraries of gates that people use for designing often have these kind of structures because they're commonly used. So the question then becomes, let's try to find, let's say, TDAS. Do I already have it solved? Okay. So I'm trying to find TDAS. This is one path between A and S. This is a green one is the other path between A and S. Do I have any other pathway between this? Technically, you can imagine that I can take the yellow path up to this point and then switch to the green path. So there are actually 4 paths that kind of exist out here. But for each one of them, I can calculate what the delays are going to be through it and calculate the minimum and the maximum. I'm going to let you work it out. I mean, it's just a lot of bookkeeping which is happening out here. So I basically kind of keep track of delays from each possible sort of input to each possible output. Do that on min and max formula that we kind of talked about. I'm going to skip that one and kind of okay. I don't have the answer out here, but this will probably be a homework problem. Yeah.
For the OAI thing, for the yellow pad, since it only goes through the OR gate, is the total delay still 120?
Yeah, it's 120 for the whole. And the reason again has to do with the way these gates are designed in transistor level. So here, even though it seems to you that yellow path is going through just one gate and the green path is going through 2 gates, in reality deep down at the transistor level, that distinction is not there. It's not as if this thing is made using 2 gates. It's actually a single gate. Question? Oh, okay. So by enumerating these paths, one can basically begin to find these contamination delays and propagation delays. Okay. What about an n-bit adder? So let's say I have a full adder, and let's say the delay is 1. What do you think is T propagation delay from A to S? So here S means across all the bits, right? So we are basically saying for the full adder, between any pair of inputs, the delay is 1. Okay, so let's say we kind of make that simplifying assumption. In reality, it's not as the previous few slides would have, but let's say it is the case. Then what do you think is T dash? The propagation delay from A to S.
Are you talking about the highest S or the lowest?
All that. So I'm looking at S as a bus, right? So S is an n-bit signal. A is an n-bit signal. So propagation delay would, so let's assume all bits of A change at the same time. Okay? And now I'm looking at those n bits of S, and I have to decide from the latest change in A, any of the bits of A, what is the latest change in any of the bits of S?
1.
1. Okay, so they vote for 1. Propagation delay. N, right? Because I'm going to go through all of these. Change in here, sort of in series going up out here, right? So this is going to be N. What is TCAS going to be? So from contamination from A to S.
1.
That's going to be 1. What about delay from carry to sum? Again, N. Carry to carry, what would be that? So delay from carry, so carry is this guy, right? So change out here to the earliest change in C out or the latest change in C out, right? I mean, that's what we are looking at. So in this case, actually, it will be both of them will be N because they still have to go through it. But this is because we kind of assume that the contamination delay and propagation delay for full adder will always 1. In reality, there would be something different.
Can you explain why the contamination for A to S is 1?
This one, CA to S? Well, look at what will happen through this path. It will contaminate, I'm sorry. This path, right? And the many such paths. TCCS is contamination from C to, oh, I'm sorry, you're right. Okay, you're right. So TDCS is contamination from carry to sum. So that would be N, which would be this path. And carry to sum contamination is going to be this path. Yeah, so this is going to be TCCS, so this will again be 1. Yeah, thanks. So basically, finding these contamination and propagation is kind of a lot of bookkeeping that we have to do, following kind of really 2 main rules. In series, you add them up, and then you enumerate all the paths and add, and then take the minimum for contamination delay, minimum across all the paths for contamination delay, and maximum across all the paths for propagation delay. And you kind of keep doing this process recursively. So that gets us the delay characterization. So main thing remember is contamination delay is not the same thing as the minimum delay. Okay, that's an important point to remember. Contamination delay is really the minimum amount of time from an input signal delay to the output signal delay. Okay, whereas on the other hand, minimum delay is the minimum amount of time from an input change to an output signal taking its correct value. Okay, so the subtle difference, right? I mean, in one case we are saying so contamination delay is input changing to the earliest time output changes, but not necessarily to a valid value. Whereas minimum delay refers to input changing to the output changing and being valid. Okay, so the two are different things. So again, keep that in mind. Propagation delay, on the other hand, is basically saying what's the maximum time it takes from an input change to the output stabilizing to its valid value.
So what's the minimum delay for n-bit adder? Is it
Actually, minimum delay is something that we were not keeping track of at all, but it is at times useful, right? I mean, minimum delay can tell you, for example, how fast can I like usually propagation delay might be a function of time, for example. Sorry, a function of temperature. So it may be that when my chip is hot, propagation delay is higher, when chip is cold. So manufacturer may say, across the operating environment, at this temperature, you might see this propagation delay, at that temperature, you may see. That's one thing. The other thing what happens is when you make chips, they are not identical, okay, because the transistors are fabricated using chemical processes. So 2 copies of the same chip, they actually have different delays. So the manufacturer may say the delay of this signal, the delay of this chip may range from 100 to 120. So what that is really saying is propagation delay can range anywhere from 100 to 120. Okay. Contamination delay is often also specified because it's also needed. we'll see how it kind of gets used.
So is minimum delay generally longer than contamination delay?
Is minimum delay generally longer? Yeah, stands to reason, right? I mean, if it was shorter, then that would be the contamination delay.
Right? You explain the TDAS.
Sure. So TDAS is referring to propagation delay from A to S, but A and S are both n-bit signals. Okay. So now let's imagine A changed, all the bits of A changed, and the question is how long before S has stabilized. Another thing is how long before all the bits of S has stabilized. Right? So our worst case would be that a change in A out here has to propagate through all of these before the stabilization happens. Imagine I'm adding, imagine that B was all ones, and A was, and C in was 0 and A was all 0. And then I changed the last bit of A to 1, as in the least significant bit to 1. So now my carry will propagate through, right? 1, 1, 1, 1 plus 1. So I'll keep having carries, and eventually that effect of the carry will be felt in the outputs.
So that depends how you define TDS. And I say if I keep all the lower bits constant and I change the MSB of 8, then the TDS will
But again, I have to be prepared for across all possible values, right? So A is a multi-bit signal, D is S is a multi-bit signal. Across all possible pairs of all possible scenarios, I have to make sure that it's true. So the worst case would be one where the carry kind of propagates through all the bits. Any further questions? Yeah.
delay is not equivalent to propagation delay.
Pardon?
Maximum delay is not equal to the propagation.
See, don't confuse the maximum and because maximum and minimum are referring to when a circuit has some variations because of temperature or because of manufacturing or something like that. Okay, so that's why they use the term contamination propagation delay, because contamination is under current condition. What's the earliest time it can change and what's the latest time it will take to stabilize?
Maybe is there a timing parameter for the first change in the input to the last settle of the output?
There is none, and the reason is it's not very relevant. It turns out you will see, not today, but next time around, that when we design sequential circuits, it turns out that this contamination delay is actually a major problem. And the reason is the following, intuitively. Remember again, so what we have is flip-flop, combinational logic, another flip-flop, right? What you also, now the way the flip-flops work is the following. Flip-flops like to have the input stable a little bit before the clock and a little bit after the clock also. So this goes back to the question you were asking, which is what happens if the input to the flip-flop is changing at the same time as the clock edge is coming. Bad things happen, and so each flip-flop has something called a setup time, which says input should be stable a little bit before the clock edge. And there are also something called hold time, which says input should remain stable a little bit after the clock edge also. Now imagine what may happen is that if the contamination delay of my combinational logic was too short. So when the state register changes value, the effect of that value, because of a very small contamination delay, can race through my combinational circuit and hit the state register while I'm still in that hold period, where the flip-flop would like to see a stable value, but because of a very short contamination delay, we kind of race through this thing. So it turns out that in modern circuits, if your delay is too much, let's say your propagation delay is too much, I can take care of it by slowing down the clock. Okay, I just at some slow enough clock speed, the propagation delay is going to be taken care of. Contamination delay becomes to be very nasty because if I have very short paths through my combination logic, then they may reach the flip-flop while flip-flop is still in that range where it wants the input to be stable. And then really problematic happening because you have to somehow find out what are the really fast paths to my logic and kind of take care of them. So it turns out currently in design, when design these steps, these fast paths, the contamination delay is not serious. So anyway, we'll continue this discussion next lesson.